these are the notes for 4-5, and the title of this is called You Can Build It. So this is kind of contextual. We're going to give you a scenario, and the idea is that we can model the scenario mathematically and solve it then to find the possibilities for the answers. So this scenario is Lindsay's going to install a rectangular patio. She has enough concrete to create a patio that is 168 square feet in area, and she wants to hang twinkle lights around the entire perimeter. And she has 52 feet of twinkle lights. Okay, so I'm talking about two things. I'm talking about area of concrete, and I'm talking about a line of twinkle lights. So I've got it highlighted in separate colors, just to, so that we can distinguish between area and the lineal feet of twinkle lights. So the best thing to do is to start out with kind of a sketch. So if here's our rectangular patio, then that patio has a length and a width. So maybe that's the width and the length. And then we're going to put these twinkle lights around him. So we're going to string these lights tight so they hug the patio exactly. That's really the only way we can create a mathematical model, is if this looks geometric. So here are my twinkle lights. So they're going right around the perimeter of the patio. So first thing it's saying is, let's develop a model to describe the area of a patio. Okay, so we know that a rectangle area has length times width. So this is length times width, and we know that the area is it's a constraint. It's 168 square feet. So in other words, it's limiting us. We have to have that square footage. And then it says list some points that satisfy this equation. So if we think about some points that satisfy this equation, just looking at that number, I know 8 goes into it. So 8 comma 21, it looks like. And I can flip-flop those, right? I can go 8 times 21, or I can go 21 times 8, right? And get lots of points really quickly. What else would go in here? 12, I think, goes in there. I'm just looking at the factors of 8 and 21. I see a 4 and a 3, so 12's got to go in there. So
at this time, our club and
so
academic
12 times, let's see,
this
it goes 1
Arts Club and academic
and 48, 12 and 14, and again, we can swap those. We can go 12 times 14 or 14 times 12. So we can come up with pairs kind of quickly. Okay, let's move on to the perimeter. So it says write an equation for the perimeter, describing the perimeter of the patio. So we know the perimeter then is, we're going to go, this length times this width, plus this width, plus this length, plus this width. So we have 2L plus 2W equals 52. Okay, and so again, they're asking you to list some points that satisfy this equation. So I'm just picking out, general points. What if the length was 12? So 2 times 12 is 24. Take that away from 52. From 52, 8. That's 28. So 12, 14, and 14, 12, right? Because we can flip-flop the L and the W and get the same 52. And ironically, I didn't even realize it, but check that out. Those numbers work in both. Let's pick some other ones. How about, I just picked any number, but let's say 10. So 2 times 10 is 20. Subtract that from 52 is 32. So 10 and 16 also work. So we can make those pairs. Whoops, I need to flip-flop those, right? We can flip-flop the 16 and the 10 as well. Okay, so we can make pairs pretty quickly. But really what we have is a system. We've got this first equation, which is L times W equals 168. And then we've got this other perimeter equation that says 2L plus 2W equals 52. And we can solve that system and come up with the solutions algebraically. But let's look at the graph. We've got enough points up here to graph this. So I've got numbers in the 8, the littlest is 8, biggest is 21. So I think what I'm going to do is I'm going to count by tens here. And that way each one of my boxes is 2s. And let's just call this L and W. Okay, so let's plot a couple of these points and get this graph here. So let's get, let's see, 12, 14. So over 12 up 14, over 14 up 12, over 10 up 16, over 16 up 10. So it looks like we have a line here. Whoops, that was not a well-drawn line. Let me zoom in. A line here. There we go. And I'm going to extend that line, making sure it continues to go through those points. So coming down here, and that intercept down there is 26, and this intercept up here is 26. And I'm just pointing out those 2 points because this is 0, 26, right? Because 26 times 2 is 52, and this is 26, 0. So I think I don't want to write them that way, though. I think what I'll do is I'll just do this. This is 26. This is the x-intercept, and this is 26. This is the y-intercept. Okay, so using intercepts, I could have graphed that too. Okay, let's graph the green one. We know, by coincidence, I have these 2 points again, 12 and 14 and 14 and 12. And then I have 8 and 21. So 8, 2, 4, 6, 8 and 21, which is like here. And 21 and 8 is here. So if you notice, this dips under and back. Okay, and I really didn't do a good job. That's a little bit better. It dips under and back right in that area. So those are our 2 points of intersection. Those are solutions. Let's take a look at how we would solve this, though, using our system. So in this case, substitution would be the best. And the easiest thing to do is take that top equation and solve that for either L or W. So I am going to solve that for W equals. So I'm going to take, just take this, oops, scooch it up a little bit, give myself a little more space. I'm going to take L times W equals 168, and I'm going to divide by L. And so I'm going to get W equals 168 divided by L. And I'm going to put that in right there. So I've got 2L plus 2 times the quantity, 168 divided by L, equals 52. Okay, and so that's 2L plus, so this is what typically happens when you have systems and one of the equations is not linear, right? This one's linear, and this one is not linear. And right now what it is I don't think really, the vocabulary is not really critical, but it's nonlinear. It's a curve, right? When we have that, when we have one curving and the other one potentially not curving, we have multiple points of intersection that are possible. And so simplifying this, choose a different color here, we have 2L plus 2 times 168, that's 320 and 16, it's 336 over L equals 52. So we have to solve for this. And the easiest way to do this, and this is true with nonlinear systems, is multiply through by whatever you see in the denominator. So we see L in the denominator. So this is going to be now 2L squared plus 336 equals 52L. and I'm going to continue working the solution below. So we can 2L squared, I'm going to bring the 52L over to the left, minus 52L plus 336 equals 0. So you notice I've got a quadratic equation, so I'm going to go for factoring here. And I'm going to divide by 2. I can divide both sides by 2, because 0 divided by 2 is still 0. So this gives me L squared minus 26L plus 336 divided by 2. I got to be back at that 168 equals 0. And then so I can star this out. So let me see here. We got to equal 168 on multiplying and negative 26 on adding. And I have my L's here. And it must be two negative numbers, right? And so we got negative 12 and negative 14. I was just pulling those solutions from above. So we get L minus 14, L minus 12 equals 0. So we have L equals 14 and L equals 12. Notice we get L is 2 values, so W has the possibility of being 2 values. So if L is 14, W is 12. And if L is 12, W is 14. Right? They just flip-flop like that. So what is the real-world meaning for these points? Oops, that's not my highlighter. The real-world meaning for these points is that I could have a patio that's 14 by 12. So 14 by 12 or 12 by 14 feet. Put the little symbol there for feet. So that's the real-world meaning. So with these systems, the algebraic solutions are a tad more complicated, but they're not too bad. Okay, so for your quick notes then, we have the first learning target is graphical solutions. And just find the intersection. And that works out okay. Learning target 2, that works. That'll work out okay if your graph is accurate enough. Learning target 2 is that you can solve systems analytically, algebraically. So if you are going through the algebra, then you can get the system all solved using algebraic techniques. Those algebraic techniques involved elimination or substitution. Okay, so as you're checking for your understanding, you're going to use your graphing techniques in question 1 that we learned in the last unit. So our graphing techniques, we have a square root, we have our h and our k, right? Our a's are both 1, but we have our h and our k, which is our horizontal and our vertical offset, and then look at that parent function. And you should be getting for answers 0, 3 is one answer, and 1, 8 is another answer. These two functions will cross it in 2 locations. For this next one, we have a system of equations here. And this system of equations, if you look at it, we have a circle and a line. So we know that we're going to get 2 points of intersection there. So this one, I would use substitution like we did in the notes, right? Take this and put it in for y. And this one, when you do that in part B, solve the system, it looks like you get 2, 6 and negative 2, negative 6. So make sure that when you solve that system, you get those answers. And then with any method you'd like on this last system, excuse me. So you could do anything. you could substitute in, and I think that's probably the easiest thing to do is put this in for y. But you could also eliminate, you could also add them together. It looks like the x squares go away. So either one. But as you work through that one, you're going to get 310 and negative 310. So looking at that, we've got two parabolas. They're going to intersect.